So first of all, is there any problem regarding last class? Is there any problem regarding last class? That is where we have discussed about the failure of the classical theory, and we have introduced the Planck's radiation law. That is how, and we are deriving the Planck's law by on the on the basis of few assumptions. Where he considered that few assumptions. Number one assumption, he considered that all the bodies inside the thermal enclosure can act as a black body. That is the all the atom. Next one, all the atoms in the black body are acting as a simple harmonic oscillator. The oscillator has a particular frequency nu. The E and the energy of each oscillator E equal to each nu. That is nothing but the quantization of the energy. That is, it can absorb or emit in the form of h nu, 2h nu, 3h nu, like this way. Where h is nothing but the Planck constant. This is the most important aspect of the Planck's assumption. And lastly, on the basis of thermodynamics and statistical mechanics, he considered the number of oscillator. Thank you. He considered that the number of oscillator inside the black body is 8 pi nu square by c cube. Okay, that is total number of. On the basis of that, we have calculated the average energy. Where average energy is nothing but we have calculated E bar. E bar is nothing but the total energy by the total number of atoms. By calculating all these factors, I think we have already achieved this equation. This equation, that is h nu and e to the power h nu minus kt by minus 1. Up to this point, is there any problem? Up to this point, is there any problem? Up to this point, is there any
equipartition theorem क्या है?
Sorry.
Sir, equipartition theorem.
Equipartition, that means half kT, and for three dimension, energy distribution in three same manner, that is in x direction, y direction, and then 3 by 2 k beta t. Can you remember the formula from your class 12?
Yes,
that is energy distributed equally distributed in three all possible directions, that is x, y, z. Yes or no?
Yes, sir.
Yes, sir.
That is nothing but that. Okay. And is there any other thing? Is there any other?
Absorptive power, sir. How it is related to Rayleigh's gives that ultraviolet catastrophe?
So basically, in the ultraviolet, according to Rayleigh's equation, that is E lambda is equal to 8 pi c by lambda t power 5 d lambda. Okay. Now look at this expression. In this expression, if we go for the if we go for the value of lambda, okay, look at this value lambda. If we decrease the value, lambda tends to 0. What will happen? Lambda tends to 0 means E lambda take lambda should be infinity. Okay, but your graph shows that graph is like this in the smaller wavelength region, that is in the UV region, that is this is 0, this is something 200, 300, 400, 500, this is visible region, then the IR region, then the micro and other region. So in this region, low wavelength region, that is the UV region, this equation doesn't hold true, and for that this is called the ultraviolet catastrophe, as this formula is not valid or not matches with the experimental data in the lower wavelength region. That's why it is called the ultraviolet catastrophe. That means it is not work properly in the ultraviolet region, that is the low wavelength region. Okay. Is there any other thing?
In e to the power h nu by kt, sir, is h nu less than kt?
Sorry?
Sir, in e to the power h nu by kt.
E to the power h nu by kt. हाँ.
Sir, is h nu less than kt?
किसके लिए?
Sir, in absorptive power, sir.
कहाँ पर absorptive power किसके लिए? नहीं, अभी हम लोग खाली डिराइव कर रहे हैं प्लैंक्स लॉ. बाद में जाके प्लैंक्स का लॉ सही है कि नहीं उसको बाद में देखूंगा. अभी यहाँ तक ठीक है कि नहीं?
हाँ सर ठीक है.
ठीक है? Okay. Is it clear to everyone? So I'll start from the next, then I'll start the recording. Okay. Chalo. So I think up to this point there is no, up to this point that you don't have any problem. That is the average energy is nothing but total energy by number of molecules. Okay. So if I ask you right now, what will be the total? What will be the that number of oscillator we have also derived that day? That is the number of oscillator is nothing but n. This number is nothing but 8 pi mu square by c cube. Okay, can you remember this formula? That is the 8 pi mu square and c cube. This one is the number. So if I ask you, that is what is the total amount of energy radiated within this? That the radiant energy, that the energy radiant energy within the frequency range nu to nu plus d nu. Within the frequency range nu plus d nu. This is average, this is total number. So this is obviously in nu d nu is nothing but n into e bar. Yes or no? Got my point? Yes or no?
Yes, sir.
Yes, sir.
और यहाँ पर d nu था number. Okay, that's all. What will be the value then? What will be the value then? N. N is 8 pi mu square by c cube epsilon. This is e curly e bar, that is means upper one, h nu by e to the power h nu by kt minus 1 into d nu. Yes or no? Is it clear to
Yes, sir.
everyone?
Yes,
Is
sir.
it clear to everyone? So what does it mean? Nu square, nu into nu cube. So the formula comes 8 pi h nu cube by c cube. 1 by e to the power h nu by kt minus 1 into d nu. This is nothing but the Planck's law in terms of Planck's radiation law in terms of nu. This is the Planck's radiation law in terms of nu. This is the Planck's radiation law in terms of nu. This is the most important formula for your entire quantum mechanics one. This is E nu d nu is nothing but 8 by h nu cube by c cube 1 by e to the power h nu by kt into d nu. This law is known as Planck's radiation law or Planck's law for energy radiation of black body. This equation is known as the Planck's radiation law or Planck's law for energy density of a black body. Okay, now this part, is it clear to everyone? Is it clear to everyone? Okay, but some of you have not read this formula, as maybe some of you have read in terms of lambda. So what is the relation between lambda and nu? What is the relation between lambda and nu? Obviously nu equal to lambda, what will be by nu equal to c by lambda. Yes or no? Nu equal to
Yes,
c
sir.
by lambda. So if I ask the same question, what is the value of e lambda d lambda? Then what does it mean? That means I have to, instead of nu, I have to place the lambda and I have to place the d nu also. So what is the value of d nu? D nu, can I say this one is the c by lambda square mod into d lambda? Yes or no? Yes or no?
Yes.
Yes, sir.
Or you can take the total level. So there should be a minus, but I am not taking that one. So what will be the value? If I take the, that is the radiant energy in terms of nu, from nu plus d nu. So same equation, the Planck's radiation law in terms of lambda, that is from lambda to lambda plus d lambda. From lambda to lambda plus d lambda. From lambda to lambda plus d lambda. What will be the value then? 8 pi hc. 8 pi h c cube. Done. Lambda cube means c cube by lambda cube. Yes or no? Got my point? E to the power h nu by kt. E to the power hc by lambda kt minus 1. What is the value of d nu? D nu is nothing but c by lambda square d lambda. Yes or no? Is it clear to everyone? Is it clear?
Yes,
to
sir.
everyone?
Yes, sir.
Look at this. C cancel out. This is lambda to the power 5. So the formula comes 8 pi hc by lambda to the power 5, 1 pi to the power hc by lambda kt minus 1 d lambda. Yes or no? Is it clear to everyone? Okay. These two formula you have to remember for the entire semester. These two formula is very crucial for quantum mechanics and the classic and the statistical mechanics also. This is nothing but the Planck's radiation law in terms of frequency and in terms of wavelength. Is it clear to everyone?
C by lambda square টা কোথা থেকে এলো? C by lambda square
This is d nu.
না উপরে ওটা।
This is d nu. Okay. D nu you are converting to d lambda.
তাহলে C by lambda
क्या देखिए C by lambda?
ল্যামডার রেসপেক্টে ডিফারেন্সিয়েট করছে।
ও আচ্ছা ঠিক আছে।
C by lambda square. That's it. Okay. Is it clear to everyone? Is it clear to everyone?
Yes, sir.
Okay. So now most important thing is that this is the formula. This formula agrees perfectly with the energy distribution for the entire wavelength region for the black body. Okay, whatever you will see, whatever you saw, that is this experimental phenomenon, experimental curve can match perfectly according to this formula. If you plot this those points according to this formula, then you can achieve the perfect result. Okay. Now the obvious question comes. Remember from the last day I told you the Planck's Wien's radiation law and Rayleigh's law. They are active in one is in lower wavelength region. Now in the another one is a higher wavelength region. Now the obvious question comes in the mind: if Planck's law fitted well with the experimental result, okay, that means from Planck's law we can achieve every failed result. That means from this law we can easily derive the law which is only active in the low wavelength region and only active in the high wavelength region, or any other law. This is the most important and the prime basic law from where you can achieve the Wien's radiation law, Rayleigh's law, and everything. Okay, I'll not go to the detail of that much, but I will just simply show you two law, that is Wien's radiation law and Rayleigh's law. How can we achieve from this equation? Those are very simple. That's why I am showing you. You can remember other than those two, that is the Stefan. How can we achieve Stefan's law from here, or how can we achieve Wien's displacement law here? That will take much time, but maybe that will not be given in your semester. That's why I am skipping this. Okay, sure. So by right now, what is our goal? So we have discussed that this formula is the most important and the most basic formula and the most accomplished formula also. That with this formula we can achieve every possible result whatever we are observing in the black body radiation curve. Now the question, as I said, the question arises: if this is the perfectly fitted with everything, can we derive the Wien's radiation law, or can we derive the Rayleigh's law from this one? Okay, so let's start with this one. This from Planck's law. Let's derive Wien's radiation law. What is that? Wien's radiation law. Remember, I told you that one, that is the E lambda d lambda is equal to A by lambda to the power 5 to the power minus beta by lambda t into d lambda. Remember, I told you in the very beginning, that is in the last class, you don't need the derivation of this one, but this formula. If this formula, and I told you this formula is only active in the low wavelength region. Okay, this formula is only low wavelength region. So let's check whether if we put the low wavelength here, then we can achieve this formula or not. We can achieve this formula or not. For the value of low wavelength or low temperature, for the value of low wavelength and low temperature, what will be the value of this? If the value of wavelength is low and value of the if lambda is low or T is low, then what will happen? What will happen? This quantity will be very much high, yes or no? e to the power this flow, then means this quantity will be high and e to the power will be much higher. Yes or no?
Yes, sir.
Yes, sir.
So in that condition, can we neglect the -1? If this quantity is higher, then can we neglect this one? Surely we can neglect this one. Yes or no? Look at
Yes,
this.
sir.
Yes.
If the
Yes,
value
sir.
of lambda is very small or t is very small, this quantity will be higher. So this quantity will be very high as compared to -1. So we can ignore that -1 from the denominator. Yes or no? If we remove that -1 from the denominator, then what is the expression? Removing -1 from the denominator, what will happen? What is the formula then? E lambda d lambda is equal to 8 pi hc by lambda to the power 5. Look at this, -1 is not there, so that means e to the power minus hc by lambda kt. Yes or no? Into d lambda. Yes or no?
Yes, sir.
Yes, sir.
यहाँ पर -1 को हटा दिया, ये पर ये नीचे था, ये ऊपर गया, इसलिए माइनस आ गया. Is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. सर वो क्या लिखा है? If
Removing -1 from the denominator, as this quantity is very high in low wavelength and low temperature. Yes or no?
Yes, sir.
Okay. Is it clear to everyone?
Yes, sir. Clear, sir.
Yes, sir.
Yes, sir.
Okay, so what does it mean? Now look at this. 8 is a constant quantity, pi is a constant quantity, h is a constant quantity, and this one is a constant quantity. So this is a complete constant. We are considering this as a same. Okay, and look at this. H is a constant quantity, c is a constant quantity, k is a constant quantity. That is also another constant. Say this is my b. So look at this. The formula is coming. E lambda d lambda is equal to a by lambda to the power 5 e to the power minus b by lambda t d lambda. Yes or no? Got my point?
Yes, sir.
Yes, sir.
This is nothing but the Poincare radiation law. Is it clear to everyone? Is it clear to
Yes, sir.
everyone?
Oh, yes, sir.
Look at this. This is the most general formula from where you can achieve everything. So this Poincare radiation law, which is active in the low wavelength region, that can be achievable with this help of the Planck's law. With simple approximation, we can achieve this one. Okay? Is it clear to everyone? Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay, so if I go for the next one, that is also simple. That is also simple. Okay, so with this law, I have to derive the second one, that is the Rayleigh-Jeans law. Okay, second one, that is the Rayleigh-Jeans law. Okay, second one, Rayleigh-Jeans law. What is Rayleigh-Jeans law? Rayleigh-Jeans law is 8 pi. Remember, what is Rayleigh-Jeans law?
8 pi kt by lambda
8 pi kt
4 into d lambda.
lambda to the power 5.
4.
Lambda to the power 5.
Lambda 4.
Lambda to the power 4 into d lambda.
Lambda to the power 4 into lambda to the power 4. Sorry. Lambda to the power 4 into d lambda. D lambda d lambda. Okay. And we told you we have already discussed this is only valid in the higher wavelength region. So for higher wavelength region.
sir, how lambda 4?
Sorry,
So lambda should be 5 na power.
lambda to the power 4. Rayleigh-Jeans law. यहाँ पर lambda नहीं है.
Sorry, sorry.
ठीक है ना? So in higher wavelength region or high temperature, just give me 1 second. Just give me 1 second. Hello. Just give me 1 second. So there is exam is going on for the second year, third year. So I have to arrange them. Just give me few minutes. Okay, sorry. So, okay. Chalo. So, up to this at high temperature, at higher wavelength and the high temperature, the value of this should be this formula should be transformed to this. Now look at this. If the value of high wavelength is high or the temperature is high, can you tell me what should be the value of this one? This should be very, very small, yes or no? If this is the point, then if this quantity is very, very high, then it should be very, very small, yes or no?
Yes.
Yes, sir.
Yes, sir.
Lambda high, T high, so this quantity is very small. So can we say that this is nothing but e to the power series of e to the power x, where x is very small, yes or no? It's a series of x to the power x, and the value of x is very small, yes or no?
Yes, sir.
Yes, sir.
What is the value of the e to the power x series? What is the value of the e to the power x series? If x is very small, what is the value of the e to the power x series? Anyone? If the value of x is very
1 plus x plus x
Sir,
square.
1 plus
plus
x plus 1
x
by
plus
x.
x square by 2. Yes or no? Is it clear to everyone or not?
Yes, sir.
Yes, sir.
Yes,
1
sir.
plus x square by 2 like this one. So look at this. Lambda is very small. Lambda is very high. T is also very high. So this quantity will be again very less. So we don't have to consider this one. So look at this. Only two part is there. So in this expression, 1 by e to the power x c by lambda kt minus 1. Can I write this one? 1 by 1 minus plus hc by lambda kt minus 1. Yes or no? Ignoring the higher order term. Is it clear to everyone?
Yes, sir. Yes, sir. 1 1 कट जाएगा lambda के
और कट जाएगा, क्या आ रहा है?
lambda t ऊपर जाएगा.
hc by lambda kt. So ये आ रहा है lambda kt by hc. So this equation is coming lambda kt by hc. Yes or no? Is it clear to everyone? Is it clear to everyone? So look at this. In this expression, this portion should be transformed to lambda kt by hc into d lambda. Yes or no? I have put the value of e to the power this value here. So this one, is it clear or not? Is it
Yes,
clear
sir.
or not?
Yes,
So
sir.
why that higher is ignored in
Sorry,
denominator?
Renita, go ahead.
So why that higher term is ignored in denominator?
If this one, x is nothing but hc by lambda kt. If the value of lambda is high, square of that one, this quantity will be very, very less, yes or no?
Oh, yes, yes.
Okay. So what is the value? That is
lambda
lambda एक
कट
कट
जाएगा.
जाएगा, 4 आ जाएगा, h कट जाएगा, c कट जाएगा. So that is nothing but how much? It is nothing
8
but
pi kt by lambda 4 d lambda.
8 by kt lambda to the power 4 d lambda. Look at this. Is it coming or not?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, by this way, you can easily predict or you can easily derive the Other's law, which is inadequate or which is not satisfactorily give an idea about the experimental result, or the failure of the classical theory can be explainable with the help of the Planck's theory. Planck's theory is Planck's radiation law is the most important and most general formula from where you can achieve all the classical law which has failed to explain the graph properly. Is it clear to everyone or not? Is it clear to
Sir.
everyone? Yeah, go ahead.
सर लेकिन वर्किंग तो सेम रहेगा ना सर, जैसे विन्स रेडिएशन लॉ शॉर्ट वेवलेंथ के लिए और
शॉर्ट के लिए रहेगा, लेकिन वो मतलब वो एक्सप्लेनेशन सही नहीं है, मतलब सही नहीं है, लेकिन एक काम ओके माय पॉइंट इज दैट we have already discussed that Wien's radiation law is not perfect, Rayleigh's law is not perfect, but why we are reading this? So basically we know that there is some kind of limitation, but at the time of discovery that was a very interesting result, that up to that point in the low wavelength region Wien's radiation law is active, in the higher wavelength region the Rayleigh's law is active. Up to the discovery of the Planck, that two law was at par, or at that point that we can explain little bit of the experimental result. But after the discovery of Planck, those two doesn't have the much importance, but you can easily check that from Planck's law, those law can be derivable easily. Okay, is it clear to everyone?
Yes, sir.
Clear to everyone?
Sir, till now we are dealing with classical or modern?
No. We have already jumped to the quantum, as we have considered that the energy is quantized right now. That is the Planck assumption, where the energy is quantized, E equal to h nu, and the absorption or the emission is happening in terms of what? H nu, 2h nu, 3h nu. That is the quantization of energy. So we already jumped our discussion from the classical to quantum, and on that basis this diagram or this graph explained properly. So Planck's law and the idea of quantization is the first point from where the quantum starts. Okay, is it clear to everyone? Is it clear to everyone?
Yes, sir.
Okay, chalo. So before going into the detail of the other part, that is all the quantum mechanical part, which cannot be explained on the basis of the classical theory, I'll just express few formula. It is well-known formula, but yeah, it is better to write it down here. Otherwise, you can miss from books. Okay, this formula, I think, very associated formula with the Planck's law and the photon. Okay, what is the energy of a photon? Energy of photon is nothing but
H nu.
Energy E equal to h nu. Okay, energy of a photon E equal to h nu. Okay, number one, what is the mass of the photon? What is the mass of the photon? Anyone?
Mass of the electron.
Sir, 9.1 into 10 to the power minus 31.
Okay.
1.6 into 10 to the power minus 27.
Okay, this is a wrong statement. At the mass of the photon, there are two kind of mass. Some of you know as rest mass and the relativistic mass. Rest mass of the photon and relativistic mass of the photon, they are two different things. Some of you have know this formula, that is rest mass, and if the body is traveling with a velocity which is comparable to the velocity of the light, then this should be m is nothing but that mass is m naught by v square by c square. Yes or no?
Yes.
Yes, sir.
Yes, sir.
So this is nothing but where m naught is the rest mass. So if I ask you mass of the photon, that question is a wrong statement. Rest mass of the photon is 0. Why? What is the velocity of photon? What is the velocity of the photon?
Speed of light.
Speed of light. Yes or no? Then V by C, what is V by C?
CC will cancel out, sir.
0
This one totally 1 minus
Sir,
1.
undefined হয়ে
ও
যাবে।
হ্যাঁ 0 হয়ে যাচ্ছে।
Both of them
Zero.
are-
0 হয়ে যাচ্ছে 0
হবে
স্যার রুটের আন্ডারে 0 হতে পারে।
রুটের আন্ডারে 0 মানে কিছুই নেই, বাজে কথা লিখেছো। Okay, there is nothing. মানে আমার
তাহলে মাস অফ ফোটন কি তাহলে?
Zero.
রেস্ট মাস
rest
ওটাই
mass,
ধর।
that is the mass of the relativistic mass is there, rest mass is 0. Okay, yes or no?
Sir, I don't know this concept. Can you explain?
Which one? Which concept?
Rest mass and relativistic mass.
That is the if the particle is moving with a velocity with the comparable to the velocity of light, then their mass is related to m equal to m naught v square by c square. Okay, that's it.
Okay, sir.
Then put the
That means if a person moves with the speed of light, then his mass will be 0.
yeah.
স্যার ওটা বাই হবে না, এম নট বাই না,
Oh, sorry, বুঝলাম না।
মানে বলছি ওটা এম নট
Sorry, এটা বাই আছে। Sorry,
এটা আনডিফাইন্ড হবে না।
this is one by. Okay. করে দেব, চাপ না। Okay, যে কি আধার নাম্বার থাকলে okay. Okay, so my point is that rest mass is nothing but m into m naught like this. Is it clear to everyone? Is it clear
কিন্তু
to
স্যার
everyone?
আনডিফাইন্ড হয়ে যাচ্ছে।
Aschi, that's why. Sorry. So this is 0. Yes or no? M naught by 0, then it is the rest. This is one is nothing but undefined. Okay. Sorry. I'll repeat once again. Then I think I have made a mistake simply. Not mistake. Mass of the photon. Mass of the photon. Okay. Mass of the photon. Mass of the photon. What is the value of this one? This one is a question now, and we have already deduced this one that the rest mass m is nothing but m naught 1 minus v square minus c square. This is the relativistic mass. Yes or no? This is the relativistic variation of mass with respect to velocity, and the velocity of the light is comparable to this one. 1 minus 1, that is 0, m by 0, this is undefined. Then how to express this one of the mass of the relativistic mass of the photon? Then how to express the relativistic mass of the photon? This is not the process, then how to explain? Okay, the process is, you know this formula, energy formula with the mass. What is the formula? The mass energy equivalent. What is the mass energy equivalent? Anyone? Mass energy equivalence formula. From your class 12 or from your childhood days. What is that?
Equivalent to mc square.
E equal to mc square. And what is E? What is E? The energy. M is the mass of the photon. And this one. So if I derive this mass of the photon, can I write it down? That is M equal to E by c square. Yes or no?
Yes, sir.
yes sir
Okay. Or in terms of this one, E equal to h nu by c square, or nu equal to c by lambda, so this is equal to hc by lambda. This is the mass of the photon. But remember one thing, this is the relativistic mass of the photon. Okay, is it clear to everyone?
yes sir
Sir,
what
if
is the-
this is relativistic mass, what was before then?
What is before? That means
M equals to m naught by root over that thing.
that is the general formula, how the mass varies with the time with respect to velocity. If you are small enough, and if you have a very small weight, you can travel with the same velocity of the light, then your mass will vary at that formula. Okay.
Okay, sir.
না বলছি তাহলে রেস মাসটা তো 0 হচ্ছে না, মানে এম
Rest
নটটা যেটা ছিল আর কি আগের বার যেটা লিখলেন, m ইকুয়ালস টু m নট।
Rest mass of the photon is 0, but how you can compare from this one? Maybe that is the question. Maybe I'll ask that question tomorrow. Okay, no issue. So Remember one thing, this is relativistic mass of the photon, and the rest mass of the photon is 0. Rest mass of photon is 0. Okay? This one is also correct. This is relativistic mass. So relativistic mass is 0. তাহলে এই ফর্মুলাটা ভ্যালিড নয় for photon. m naught 1 minus v square by v square. This is 0. So maybe this will be also 0, but it is not the case here. Okay? So it cannot be achieved by this. Okay? So what is the, if this is the energy, this is the relativistic mass, this is the mass equivalence, and what is the formula for then momentum of photon? Momentum of photon. Anyone?
F by lambda.
H by lambda, sorry.
P equal to momentum P. P means mass. What is this? Velocity. What is the velocity of photon? What is the velocity of photon? C. It's the mass velocity of light. Then what is the value? M means, that means h nu by c square, and h into c, that means how much it is coming? It is E by c or h nu by c. Is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, and one more thing, some of you have read this one or may not, I can't remember, but this derivation is not required, but that is the energy momentum relation, for relativistic particle. Energy momentum relation, anyone? Energy momentum relation, that is p square equal to p square c square by m naught square c to the power 4. Can you remember this one? Or E equal to root over p square c square by m naught square c to the power 4. You have to remember this formula. It can be derivable from using the relativistic approach, but for your purpose only the expression is required. This expression, and this expression. No derivation is required. And the other thing that if you want to arrive, this can be achievable. Okay, if you want how the rest mass is coming 0 for photon, think on that approach and you can easily achieve that point. Okay, otherwise I will take a different class and show you that all these things can be achievable with the help of the relativistic theory. Okay, got my point? Is there any problem?
Sir,
The rest mass का
sir,
concept
আমরা
समझ
mass energy equivalence থেকে কেন নিচ্ছি?
Rest mass matlab that mass does, that is the, what I say, this is my, that is the in static condition, that is the, if the particle moves in a relativistic velocity, the rest mass value of the mass will change to that one. Okay,
স্যার এটা বলুন ফোটনের মাসটা যেটা জানতাম 1.6 10 to the power minus 27 ওটা কখন হয়?
फोटोन की मास जानते?
फोटोन प्रोटॉन था यार।
ও আচ্ছা
ওটা ফোটন ছিল, প্রোটন নয়।
কিন্তু আর এই ফর্মুলা দিয়ে তো তাহলে আনডিফাইন্ড হয়ে যাচ্ছে, তাহলে স্পিড অফ লাইট এটা তো মানে ইনফিনিটি মাস।
Speed of light infinity mass. So that rest mass হচ্ছে the mass of the body as measured when the body is at rest. No relativistic approach is obtained there.
হ্যাঁ স্যার, তাহলে এই ফর্মুলাটা
Yeah, you can't give this formula 0 by 0. That is
No
not,
sir,
sorry.
I am talking m naught by 1 by root over 1 minus v square by c square. अगर रेस्ट मास है तो v तो 0 हो गया, तो m equals to m naught हो जाएगा ना वहाँ पे तो केस।
Rest mass भी कहाँ से 0?
ও হ্যাঁ, রেস্ট মাস হলে তো v 0 হবে, তাহলে তো
Yes, sir. When it
One
is
হয়ে
rest
যাচ্ছে,
mass,
শুধু m naught
then
হয়ে যাচ্ছে।
V will be 0. So M equals to M naught हो जाता तो।
की बाजी बोलছো?
सर रेस्ट मास पे तो E इक्वल टू mc स्क्वायर आता है ना।
স্যার মাসটা রেস্টে থাকলে তো v 0।
এবার বলো, what is your point?
স্যার এখানে তো v টা 0 রেস্ট মাস।
Sir, when mass, हाँ।
For that one, mass will be there. Rest mass. Rest mass, the proton and rest mass will be 0. This is the proton rest mass is 0.
Sir, rest mass will be m naught.
m naught টাই তো rest mass.
এম নটটাই তো জিরো হচ্ছে।
এই ফর্মুলাটা কাজে কখন লাগে আমি তো বুঝতে পারছি না।
It's a special formula.
It's a special formula. It's a relativistic approach. It's a relativistic approach. When the body is moving with the velocity which is comparable to the speed of the light, then this
তাহলেও তো বেরোচ্ছে না কিছু আনডিফাইন্ড হয়ে
বেরোচ্ছে না। তো সেই জন্য কোশ্চেনটা তো that we cannot deal with this formula, but every time this is a special formula. If you travel with the velocity with the which is comparable to the wavelength of the velocity of the light, your mass will vary. Suppose your rest mass right now is 37 kg and you are moving with the same velocity of the order of light. This should be 37 and that much will change.
That time it becomes undefined. So
No.
arekta formula.
No. You are going in a wrong way. It is comparable to this one. It's maybe 0.99 C. Then why it is undefined?
দুটোকে রিলেট করা যাবে না একসাথে, মানে এটা একটা ওটা একটা।
That's why I told you, you can't relate from the photon. Whatever you have
না
read
এটা
from
ফোটনের সাথে রিলেটই করা যাবে না।
just whatever you have read from your class 12 days, that is a wrong statement. Whatever you are watching for the photon, that is the relativistic one. The rest mass of the photon is 0. Look at this. Think in this way. If the mass of the rest mass of the photon is not 0, how it is traveling with the same velocity of the light?
হ্যাঁ পারবে না তো।
If there is any kind of mass, is it possible to the move with the
না
velocity?
না না not possible.
No, sir, it is not possible.
Not possible.
Then we can't mix up with this one. That's why I asked you. So this is the formula, relativistic formula. And if you consider that you are 37 kg, impossible. Maybe that is a few, few microgram or few the nanogram like this one in terms of gram, milligram is beyond that. It is in a very small. Then only this equation is valid. Okay. So whatever you are observing for the photon, the rest mass is 0. That's why you are saying that it is comparable to the velocity of light. That is of the order of c. Yes or no?
Yes, sir.
So means m not having a sum value.
M not?
m not having a sum value.
किसके लिए?
सब उसी के लिए, मतलब लाइट की स्पीड से वो ट्रेवल कर रहा है तो उसका कुछ वैल्यू है मतलब।
हाँ नहीं, वैल्यू कैसे रहेगा? अगर वैल्यू है तो m not कहाँ रहेगा?
Sir, hypothetically, if we travel
सर
with
রেস্ট মাস v ইকুয়ালস টু c যদি হয় তাহলে m ইকুয়ালস টু m নট বাই 0 হলে আনডিফাইন্ড কেন হচ্ছে না?
So we cannot consider photon approach, that is the mass of the photon with this formula. Okay, that's we have to go for different ways.
স্যার এটা তো লরেন্স ফ্যাক্টর, তাহলে এটা ইলেকট্রন প্রোটনও লাগে।
And electron proton, obviously this is valid for the electron proton. But my point is, look at this. You are saying a photon. Photon is nothing but sometimes you say quanta of light. Yes or no? If it is a mass, how can it travel with the same velocity?
না।
মাস লেস তো স্যার না।
You are saying, yeah, thank you. But Oindrila, my point is, it is a massless, but it's a rest massless, but there is some relativistic mass. Otherwise, this momentum is not possible. E equal to mc square, this is not possible. P equal to mc, that is also not possible. Whatever we have derived, that is the Planck's radiation law. That is nothing but the quantization of photon. It has some energy. Yes or no? Particle, if it is a particle, then only this can be achievable, no? That the momentum, energy. Other than that, it is not possible.
হ্যাঁ তাহলে মাস কম হতে
Look at this. Velocity is in two different ways. That is, we are saying that photon is traveling with the same velocity of the light. Okay, so that means we have to consider that mass is very small or mass is 0. Again, we are considering that when light falls on any parameter, it creates we feel some pressure on the substrate. Yes or no? That is the energy is giving to them. That means it has some sort of mass.
হ্যাঁ
So then where is the fallacy? The fallacy is here that the mass, whatever we are saying for the energy, that is not the proper mass. That is not the rest mass. My weight is 48 kg. Your weight is right now maybe 37 kg or something like that. You are at rest, and that is your rest mass. The photon is moving. So for that purpose, we have to consider the relativistic mass. Yes or no? What my point?
তাহলে আমরা যে বলি যে মাস অফ দা ফোটন হচ্ছে 10 টু দি পাওয়ার -50 এর অর্ডারে থাকে, তাহলে ওইটা কোন বেসিসে বলা হয়, মানে কোন
আর না হলে মোমেন্টামে
That is the value of the relativistic mass.
আচ্ছা
আর না হলে মোমেন্টামের টাইমে আমরা তো
Not
ফোটনটাকে পার্টিকেল ধরতে পারি।
yeah. M naught is very, very small. Then only look at M naught, whatever Anindo said at that time, that we know the value of the proton 9.1 into electron 9.1 into 10 to the minus 31. Remember?
yes sir
Yes, sir.
That is also
Yes,
rest
sir.
mass. That is also rest mass. But electron doesn't travel with the same speed with the light.
না
Sir, an
স্যার
object.
তাহলে
But we can use this formula for the electron. Why? As
because electron is not traveling with the
Electron
speed of
at
light,
least
তাই জন্য
mass of-
undefined হচ্ছে না।
B is
তাই জন্য।
almost comparable to that one. Okay, comparable. My velocity is far, far less. That means very, very less than comparable light. But electron, the velocity of electron can be comparable to this one. Yes or no? That
Yes,
time you can use this one.
Yes, sir.
What my point?
আমরা স্যার রেস মাসটা আমরা কিছু কিছু পার্টিকুলার ক্ষেত্রে ইউজ করতে পারবো, ওই বাকি যেটা আছে ওটা আমরা সব জায়গায় ইউজ করতে পারবো, তাই তো?
For the rest mass concept will not come. Rest mass concept or rest mass, this formula cannot be expressible for the photon. Okay, what my point?
Sir, an object is at rest with in comparison to something, sir. So
Yeah. Which is moving or not? That should be the inherent property of the body. Okay.
yes. So in light, in the case of light, with what respect are we saying it is at rest or it is, sir,
We
moving?
cannot say that, na. That's why you can say that rest mass.
স্যার আর আপনি বলছেন যে স্ট্রাইকের সময় রিলেটিভিস্টিক মাসটা কনসিডার করা হচ্ছে, তাহলে রিলেটিভ মাসটা কোনটা, মানে কত হয়?
কত মানে ক্যালকুলেট করতে বলেন, ক্যালকুলেট করতে হবে।
স্যার
ওটার জন্য ওই এনার্জি
one
ফর্মুলা
question.
লিখে দেবো।
ওটা
Equal
দিয়ে
to
use
mc
করতে
square,
হবে,
that is the E by C, that is equal to h. বলো।
স্যার তার মানে ওই as photon is traveling with the speed of light, তাই জন্য রেস্ট মাসটা মানে ভিটা তখন সি হয়ে যাচ্ছে, তাই জন্য রেস্ট মাসটা আনডিফাইন্ড হয়ে যাচ্ছে, ওই জন্য আমরা ওই নতুন ফর্মুলাটা ইউজ
Yes,
করছি,
no,
m equals to
undefined
e by
হয়ে
c
যাচ্ছে।
square।
We're going in a wrong way. I told you that my rest mass of the photon is 0 and this also 0, so 0 by 0.
আনডিফাইন্ড হয়ে যাচ্ছে
So
তখন,
that is not possible.
সো ওই জন্য আমরা একটা নতুন ফর্মুলা
This
করে
is not
নিয়ে
rest mass, this is relativistic mass. This is relativistic and this is rest. দুটো আলাদা জিনিস। What we are achieving that relativistic, it is coming from this expression, it is coming undefined, so we are going for a different approach. What my point?
হ্যাঁ স্যার বুঝেছি।
Is it clear to you? Problem কোথায় জানো? Problem হচ্ছে you have not read the relativity. Okay, that is the relativistic approach and the relativity of Einstein relativity.
Yes, sir.
Initially that was in the syllabus, but right now
That
they
to
are-
vary with frame.
sorry.
Sir, relativity always vary with the frame.
Yeah, dependent on the frame, always varies. If you are in the inertial frame, I am also inertial frame, and both are with the same condition, then that will not vary. So that will be you have checked this one. Maybe this you don't have to read you can read from the book or you can read from the internet. There is called time dilation. Moving clock runs slow.
Sir, that
Time dilation. Then there is called
Not difference.
then there is called length contraction.
And that is Lorentz transformation, sir.
Exactly, Lorentz transformation. All this happens due to that relativistic approach. But I can't take the class here right now. So some of you have as the say a twin,
paradox.
Twin paradox. That is also for the relativistic. All those kind of formula can be achieved from can be used or can be done in the relativistic domain. But we can't go for that one. So I have just given you an idea from where MCQ can come. That is the energy of the photon is E equal to h nu. Relativistic mass of the photon, rest mass of the photon is 0. Relativistic mass of the photon is m equal to h by c lambda. Momentum is also E by c, and the energy mass equivalence E equal to mc square, and the energy momentum relation E equal to p square c square by m naught square c to the power 4. Okay, got my point? Is it clear to everyone? This
Sir, the different approach we are using is equals to mc square to find the mass of photon.
E equal to mc square, that is nothing but the mass energy equivalence.
सर फोटॉन्स का सर पार्टिकल नेचर भी होता है और वेव नेचर भी होता है, वहां पे रेस्ट मास वैरी नहीं करता है,
वहां पर इसलिए मास आ रहा है ना, पार्टिकल नेचर आ रहा है, मतलब दैट पार्टिकल हैज टू बी हैज सम सॉर्ट ऑफ मास.
हाँ वही तो,
वही मैं बोल रहा हूँ, बट दैट मास शुड बी रिलेटिविस्टिक मास, नॉट रेस्ट मास. हाँ कि नहीं?
बट सर अगर हम मान लें कि रेस्ट मास 0 है, बट फिर भी तो सर वो लाइट के स्पीड से मूव कर रहा है ना.
रेस्ट मास 0 है तब जाके लाइट के बराबर निकलेगा ना. अगर रेस्ट मास का वैल्यू बहुत कम है, that means of the order of 0, then it can travels with the same velocity ना.
हाँ बट
बोलो कुछ बोलो कॉन्ट्रडिक्शन आएगा.
सर लाइट का मास होगा कि नहीं होगा?
नेक्स्ट डे बोलेंगे, तो आज थोड़ा समझ नहीं आ रहा.
हाँ तुम पूछ रहे हो मेरे को.
सर आई हैव अ क्वेश्चन.
क्वेश्चन क्या है? क्वेश्चन है फोटोन का मास है कि नहीं. द आंसर शुड बी रेस्ट मास शुड बी 0, बट द रिलेटिविस्टिक मास शुड बी देयर. गॉट इट? एज सिंपल एज.
Sir, if we isolate a photon, then the mass will be 0, sir.
Rest mass will be 0. For relativistic mass will be there every time.
But
relativistic
mass it will move with a velocity certain.
हाँ, फोटोन को क्या करोगे? फोटोन को मतलब तुम बोल रहे हो कि आइसोलेट करके तुम्हारे पास रख दिया.
Sir, hypothetically
0 बनेगा, क्योंकि that time you are considering the rest mass.
এটাই প্রবলেম হচ্ছে. দেখুন রেস্ট মাস মানে মাসটা মুভ করছে না.
Rest mass means with all possible velocities at rest.
হ্যাঁ মানে ভেলোসিটি নেই এক কথা.
Velocity 0.
হ্যাঁ তাহলে তখন 0 হচ্ছে. আর রিলেটিভিস্টিক যে মাস হচ্ছে কিন্তু তাও ট্রাভেল করছে.
সরি,
রিলেটিভিস্টিক মাসে বলছেন মাস থাকছে কিন্তু তাও লাইট স্পিডে ট্রাভেল করছে.
হ্যাঁ
ট্রাভেল করছে বলেই তো মাস আসছে, ট্রাভেল করছে বলেই তো মাসটা আসছে,
ট্রাভেল করছে বলেই তো রিলেটিভিস্টিক মাসটা আসছে.
ফোটনের পার্টিকেল নেচারের জন্য মাস তো থাকতেই হবে.
মাস থাকলে স্পিড অফ লাইট অ্যাটেন্ড করা যাবে না.
না, যখন স্পিড অ্যাটেন্ড করে তখন তো মাস ইনক্রিজ হতে থাকবে.
যদি স্পিডটা দেখো, রেস্ট মাস ইজ 0, সাপোজ কোন কিছু একটা ইলেকট্রন, if it is moving with the velocity, then what will happen? This will appear, no?
হ্যাঁ.
But in your case, that is the photon, there is only relativistic mass, no rest mass.
হ্যাঁ.
Our particle ta, as the photon is moving with the same velocity as of the light, then there will be the what I say, relativistic mass. ভালো করে বোঝো. There are two parameters. One is rest mass, one is relativistic mass. Rest mass for photon is 0 as it is traveling with the velocity with the light. If you don't know any kind of formula, then it is not possible that rest mass will be 0. If it is rest mass is higher, then it is not possible to move with the same velocity. So that's why we are considering the approach. What is then? Photon is a particle. That is the particle nature is there. So if it is a particle nature, then it has to be some mass. Then what is the mass? That mass. That's why we have named different name. That is the relativistic mass. বুঝতে পারলাম?
Yes sir.
Clear na clear no? Anyone?
सर 70% क्लियर।
बोलो 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 नहीं
नेक्स्ट
क्रॉस
निकल
करो
नेक्स्ट
और आज
नहीं
नहीं
नेक्स्ट डे
होगा
मतलब आज नेक्स्ट डे
सर
पूछेंगे सर तो आज पढ़ के।
हाँ बोलो ओके 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 एक काम कर रहा हूँ नेक्स्ट डे शुरू में ये भी बोलूंगा लेकिन कोई भी प्रॉब्लम नहीं है मैं बोलूंगा ठीक है तुम लोग सोचो कि रेस्ट मास को जीरो कैसे दिखाओ तब हो जाएगा दो क्वेश्चन सोचो इसके बारे में तो हो जाएगा तुमको और फोटोन का रेस्ट मास जीरो क्यों है क्वेश्चन नंबर 1 फोटोन का रेस्ट मास जीरो क्यों है ये सोचो खाली और कुछ नहीं जहां पर भी ढूंढ सकते हो ढूंढो
কারণ ফোটন তো স্পিড অফ লাইটের
Massless.
ইম্পসিবल।
सर क्योंकि वो स्पीड ऑफ लाइट के साथ ट्रेवल करता है उसके पास मोमेंटम है और एनर्जी है लेकिन मास नहीं है अगर मास रहता तो स्पीड ऑफ लाइट के साथ ट्रेवल करता ही नहीं
ठीक है
इसलिए वो
एक है हुआ प्रिंस का जो प्रिंस ने बोला चाहिए फिर से बोल रहा हूँ प्रोटॉन फोटोन का एक मतलब पार्टिकल एस्पेक्ट है ठीक है पार्टिकल एस्पेक्ट
सर लेकिन एक और क्वेश्चन है सर
ये
सर जैसे कि
बोलो
जैसे कि लाइट है सर वो भी फोटोन से मिलकर बना हुआ है
हाँ।
अगर 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 फोटोन अगर मासलेस अगर होगा तो फिर वो किसी भी स्टार के ग्रेविटी से वो डिफ्लेक्ट कैसे करता है हम लोग की तरफ अर्थ की तरफ
हाँ तो इसका मतलब उसका मास है
यस सर
जब ट्रैवल कर रहा है तब मास आ जाता है।
एग्जैक्टली दैट इज नथिंग बट
ওটাই E/c²।
হ্যাঁ হ্যাঁ ওটাই।
समझ में आ
ইকুয়ালস টু এমসি স্কয়ার এখান থেকেই প্রুফ হয়েছিল।
এক্স্যাক্টলি থ্যাংক ইউ সো মাচ এতক্ষণ ধরে যেটা বুঝতে পারছিলেন so initially we are considering that it is traveling with the same velocity that means it doesn't have any kind of mass if it is there is any mass then it should be almost of the order of zero लेकिन उसके बाद जब तुमने गैलेक्सी कुछ भी सभी के पास में जब फोटोन जा रहा है तब एक कार्बेचन ले रहा है that means it has some sort of energy
Yes.
yes a momentum कहां से
স্পিডে যেতে যেতেই মাস
যখন
as it is traveling with
ট্রাভেল
this
করছে তখন মোমেন্টাম গেইন করছে।
স্যার যখন মোশনটা অ্যাটেন্ড করছে তখন এনার্জিটা আস্তে আস্তে মাসে কনভার্ট হচ্ছে।
okay that then if it is traveling with the velocity of light then what is its energy what is its mass it should be relativistic mass
हाँ
यस सर
यस सर
समझ में आया सोचो और सोचो कोई बात नहीं मैं यहाँ से स्टार्ट कर रहा हूँ This is-
এটা
और किसी अनिंदो की क्वेश्चन पे अनिंदो क्वेश्चन इज करो बाकी देर डिस्टर्ब होচ্ছে ultraviolet catastrophe is nothing but that the discrepancy in the theoretical result predicted by Rayleigh jeans and the experimental result in the low wavelength region. Low wavelength region is nothing but the ultraviolet region. As this discrepancy appear in the low wavelength region, it is known as the ultraviolet catastrophe. That's all. Okay? चलो ठीक है चलो
सर कुछ डॉक्यूमेंट सबमिट करना है ऑफिस में तो आ जाए।
हाँ आ जाओ जल्दी आज ही आना क्योंकि मैं कल नहीं आऊंगा और मेरे बगैर नहीं होगा।
আমার একটা কোশ্চেন আছে যে প্ল্যাঙ্কস রেডিয়েশন লটাকে প্রুভ করার জন্য যখন আমরা বোলস আইনস্টাইন স্ট্যাটিস্টিকের হেল্প নিই তো আরো তো অনেক ধরনের স্ট্যাটিস্টিক্স আছে তাদের কেন হেল্প নিই
কেন নিই বল
সেটাই মানে বুঝতে পারিনি ওটা মানে কেন হেল্প নিই ফেরমি ডিরাক কত আছে
ফার্মি ডিরাক কাদের জন্য ট্রু those have spin half particle that is means odd spin electron proton spin half okay
আচ্ছা
during the Bose-Einstein statistic they doesn't have the idea of electron spin okay
ওকে স্যার
স্ট্যাটিস্টিক্যাল যখন পড়াবো যদি আমি পড়াই তাহলে বোঝাবো যদি না পড়াই তাহলে টিচার হয়তো পড়াবো চল টাটা বাই
ठीक है थैंक यू सर।
থ্যাংক ইউ স্যার
থ্যাংক ইউ স্যার।
Can you hear me, students?
Yes, ma'am.
Okay.
Good morning, ma'am.
Yes, ma'am.
Good morning, ma'am. Yes.
Good morning, ma'am.
Please wait. I'll be starting within 2 minutes. Let me start the recording now. Good morning, everyone.
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Good morning. Please wait. Let me present my screen for today's class. I hope the screen is visible to all of you.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, let's start the class. I was discussing transformer. Equivalent circuit and phasor diagrams are explained. So if you have any doubts, any confusions from these two, you please raise your hand because without understanding of these two topics from transformer, it will be difficult for you to understand the further topics like efficiency regulation, etc. So if anyone is not understanding it or having any doubts, you can ask me. Okay, so I have shown you the different types of magnetic material because the selection of this magnetic material, the selection of the type of the material as core is very, very important in transformer design because many more factors, parameters are dependent on this magnetic material. So mostly the ferromagnetic materials are used in the design of transformer core that I have explained in the last week. Why ferromagnetic material? Because it has high permeability. The permeability is very high in case of ferromagnetic material. High permeability means that the conductivity of that material is very, very high in terms of magnetic flux. Maximum flux lines can be passed through a material which is having high permeability. So it's our main objective to have maximum flux to be confined within the core material so that transformer working principle can occur smoothly in order to satisfy the actual energy transfer from primary circuit to the secondary circuit. Now, let us come to this BH curve, which is a very useful characteristic curve in order to analyze the magnetic hysteresis property of a magnetic material. What is the relationship between this B and H? What is B? B is just flux density in Weber per meter square. And what is H? H is the magnetizing force or magnetic field strength in ampere turns per meter. So the curve between these two factors, B and H, of a material, of a magnetic material, is called the magnetizing curve or BH curve. You can see the shape of this curve is not linear. And this characteristic curve basically follows the law, follows the rule. Let me take the pointer first. That B is directly proportional to H. That means the flux density B produced in a material is directly proportional to the applied magnetizing force H. That means greater the magnetizing force, higher will be the flux density and vice versa. And the ratio B by H is called the permeability, actual permeability or absolute permeability mu. So the value of mu is fixed for different magnetic materials. And this absolute permeability is again defined with respect to the absolute permeability of air or vacuum and the relative permeability of a material, right? So why this mu will vary? The absolute permeability of air is fixed, but the relative permeability of the different magnetic materials are different. So based on this, mu r, basically the absolute permeability of any magnetic material will differ. So in a particular medium other than air, the flux density is equal to mu naught times mu r times H, the field strength. And for a vacuum medium, the B is equals to mu naught into H for air. And for any other medium, it's equals to mu 0 into mu r into H. So this mu r is called the relative permeability of a material, which is equal to the ratio of the flux density produced in that material to the flux density produced in air by the same magnetizing force. Okay, so these BH curves are very, very useful to analyze the magnetic circuit properly. Next, what is called the magnetic hysteresis? what is called the magnetic hysteresis, the phenomena of lagging behind of induction flux density behind the magnetizing force in a magnetic material is called magnetic hysteresis. What is the meaning of this statement? We have seen that B is proportional to H, or B is equal to mu times H, right? That means higher the value of flux density, more will be the field intensity, and vice versa. But also another term is associated with this BH curve, with this magnetizing curve, that is called residual magnetism. What does it mean? Residual magnetism. Come to this graph. This is the magnetic hysteresis graph, or BH curve, of a particular material, say for a ferromagnetic material. You can see y-axis is the flux density and x-axis is the field intensity. Okay. Now this small b, this point, small b, at this point actually what happens, though the field intensity is 0, there is a finite amount of flux density in the material. So this value of flux density OB, defined as OB as per this graph, is called the residual magnetism. That means after the removal of magnetizing force H, the material has still an amount of flux density. That means it is not fully demagnetized, though the magnetizing force is removed, though the field intensity is 0, but the material still has got some magnetism within it, that is called the residual magnetism. And due to this phenomena, what we can say is that the flux density B is lagging behind the field intensity H. The magnetic material still has the flux density of amount OB, though the field strength is 0. That means the flux density is lagging by the field intensity. This property is known as magnetic hysteresis. This phenomena is known as magnetic hysteresis. So this hysteresis or hysteresis loop is a 4-quadrant BH curve. 1, 2, 3, 4. It's nothing but a BH curve, you can see. But it has got 4 quadrants. This magnetic hysteresis or hysteresis loop, this is the loop actually. Following the points A, B, C, D, E, F, A. This is the hysteresis loop, right? And it has 4 quadrants.
May I ask something?
Yes.
Ma'am, this residual magnetism, ma'am, it happens because of the dipole arrangement of ferromagnetic material.
Yes. Yes. You are right. You are right. And that will depend upon the type of the material, right? This residual magnetism will also be different for different types of ferromagnetic materials, depending upon the dipole alignments, depending upon the alignments of dipoles of the small atomic parts inside that material.
Yes.
Okay, now this hysteresis loop is very important in transformer design because the magnetic material is important in transformer design, the selection of magnetic material, because always we'll try to select the material which will be having less hysteresis loop. Less hysteresis loop. Suppose this is a hysteresis loop for a magnetic material, say X. And this is another hysteresis loop for a magnetic material, say Y. So here material Y is having less hysteresis loop, narrower hysteresis loop, right? That means this material Y will be having less losses because hysteresis loop, the width of the hysteresis loop defines the amount of the core losses, because this loop is related to the core material, magnetic material, which is used in the core, right? And core loss is related to core only. So here core loss or the iron loss are basically the type of fixed losses in transformer, even though there are no load at the secondary side of the transformer. We cannot avoid these core losses because they will generate within the core material itself, right? So we need to choose the magnetic material. We need to select the hysteresis loop or magnetic hysteresis in such a way that the width of the hysteresis loop is small. Okay. And obviously, if the width is small, then this residual magnetism will also be small simultaneously. That means soft magnetic materials are having mostly narrower hysteresis loop. The hard magnetic materials are having wider hysteresis loop. That's why it's very much difficult to demagnetize the materials which are hard magnetic materials. Whereas soft magnetic materials can be demagnetized very easily because they have small hysteresis loop. Now, how this hysteresis loop can be formed? Let us consider a circuit. Say this is a core, the magnetic core around which windings are wrapped, and the final two terminals of the windings are connected with the variable resistance and the DC source voltage. This variable resistance is used here in order to vary the voltage, in order to vary the source current. So whenever current is rising through this coil, what will happen? Self-magnetism will be developed. So a magnetic field will be created, and because of that, magnetic flux lines will be confined within this core material from this side to this side. Right? And this field intensity, which is actually the ampere turns. Ampere turns means the ampere, the current which is supplied by this source, and turn means the number of turns used in this conductor, in this coil, right? And because of this magnetic flux lines, definitely field density, the flux density will be developed, that is B in Weber per meter square. Okay, and what is meter? What is meter here? It is just the effective length of the conductor, nothing else. Okay, fine. So in the graph, in the BH characteristic graph, this O is the origin or the starting point at which no force is given, no voltage is applied. Okay, that means just assume the circuit is not connected, the circuit is not closed, so no current will be flowing through this coil. So the situation is just the starting point, and it is just the origin in this graph. So as soon as the current starts rising through the coil, what will happen? The flux density will be also rising along with the increase of this field intensity H, right? And this is your BH graph. This is your BH graph, just like this one. So it's just a nonlinear graph following this relationship B proportional to H or B equals to mu naught mu r into h. Right? So at the point A, what happens? The current becomes steady. It's a DC source. So at point A, the core becomes saturated. That means after this point, if you still try to increase the current, there will be no change in the saturation point. There will be no more field or flux density in the core. It will remain fixed at this point with value Bm along with the value of field intensity Hm. Okay, so this is the maximum value of flux that we can obtain from this pH curve of a particular magnetic material, say for a ferrite material. So this A is called the saturation point, right? And for ferromagnetic material, the saturation point is high in order to maintain high permeability, because the ferromagnetic material has high permeability. It means that it has got high saturation point. And for ferromagnetic materials, mostly for metal like cobalt, the Curie point or the Curie temperature is about 760 degrees Celsius. That means if the temperature increases beyond this Curie temperature or Curie point for a particular material, for a particular ferromagnetic material, what will happen? This saturation point will come down to zero. The saturation point will come down to zero means the material will not be having high permeability. It will lose all its permeability when the saturation point will touch the origin or touch the x-axis. So it will behave like a paramagnetic material, in that case having very, very small permeability compared to the ferromagnetic material. That means above Curie temperature, above Curie point, any magnetic material can change its magnetic characteristic curve. Okay, and this Curie point or Curie point temperature is different for different ferromagnetic materials. Right? In practice, actually, if temperature raises above 80 degrees Celsius, the magnetic material can lose its magnetic property, which is 760 for cobalt, very much quite high amount. Okay, so what happens after this point A? If you decrease the field intensity, what will happen? The hysteresis curve, the magnetizing curve, will follow this line AB, and it will intersect with this y-axis at point B when the field intensity is totally removed, when current is exactly zero, right? But still there is a magnetism. That is called the residual magnetism. Beyond which, if you further change the field intensity, that means if you change the direction of current in the opposite way in order to demagnetize the material, you need to supply OC amount of field intensity to that winding, to that material, right? For that, you can see this curve, this AB curve will touch the x-axis at point C. That means at this point, the total residual magnetism will be finished with the field intensity in the opposite direction. So at this point C, there is no flux density in the core. Right? Now, if beyond point C, if you still increase the current in the circuit or the field intensity in the reverse direction, the core will attain its maximum flux density in the opposite direction, in the third quadrant, say at point D. The core will again be fully saturated with the negative direction of current, with the negative field intensity in the third quadrant. So it will attain minus of PM, minus of maximum flux density. So beyond this point, if you further increase the field intensity or the supply current, there will be no change in the characteristic curve. The core is now saturated. Right? And after that, again, if you vary the field in the earlier direction, in the positive direction, what will happen? Your magnetic material will again try to follow the BH curve, following the law B proportional to H, following the line DE, EF, and FA. Okay, so this time OE is the residual magnetism in the opposite direction. OE, see, at this point E, what happens actually? The flux density is there, but the field intensity is exactly 0. Okay, so this OE is again called the residual magnetism, and beyond this point E, again, when HM or the field intensity is increasing in nature, the flux density will be also rising following this line EFA. Right? So this point F is called coercivity, because at this point, see, the flux residual magnetism or the flux density is exactly 0, though the field intensity there, it is available in the material, that is of amount OF. Right? So after explaining this, what I can say that from this pH characteristic curve, following the rule B proportional to H, following many more factors like residual magnetism, coercivity, etc., one can say that always the magnetism, the flux density is lagging by the field intensity within this hysteresis loop, within this pH characteristic curve, within this all 4 quadrants of the magnetizing curve. That is called the magnetic hysteresis. Okay, and here X is the hard magnetic material and Y is the soft magnetic material. And depending on this width of the hysteresis loop, one can decide the loss to be generated within that core material as core loss, which is Fick's loss. So next, we'll move on to a new topic that is called voltage regulation. Voltage regulation and transformer efficiency. These two are very important topic in transformer design. What is voltage regulation? What is voltage regulation? The output voltage in a transformer will not be maintained constant from no load to the full load condition for a fixed input voltage in the primary. Suppose you have sent a fixed input voltage, fixed alternating AC voltage at the primary winding of a transformer, right? But the output voltage across the secondary winding will differ depending upon the loading of the transformer. If it is fully loaded, then a voltage will be developed across the load. And if it is not at all loaded, if there is no load across the secondary winding, which is also termed as the no load transformer winding, at that situation there will be no voltage across the load, though the secondary winding will have secondary induced EMF because of the primary induced EMF at the primary winding. But since the transformer secondary is not connected with the load, since there is no load, there will be no voltage across the load. So output voltage in a transformer is not constant from no load to full load condition. Now this is because there will be internal voltage drop in the series leakage impedance of the transformer. The series leakage impedance will create the internal voltage drop. The series leakage impedance will be generated because of the leakage flux. We have seen that in practical transformer, leakage fluxes are not avoidable. Those fluxes will be there, linking only one coil at a time. So these are not the useful fluxes. These fluxes are not used to transfer the energy from primary side to secondary side. Okay. And also, there is a change in power factor from no load to the full load condition. This also generates the idea of voltage regulation. Somehow voltage of transformer or output voltage of transformer requires to be regulated always, since it is not constant from no load to full load. Now this can be done experimentally by direct loading of the transformer. How to do this? Let us first energize the primary winding at the rated voltage and record the secondary terminal voltage first in absence of any load and then in presence of full load. Okay, let's connect a voltmeter across the secondary winding of the transformer. First, without the load, say the voltage recorded as V20, the no load voltage. And secondly, after connection of the load, say the voltmeter is measured a voltage of V2, that is called the load voltage. So there is a change. You will observe the change in the voltmeter readings. So difference you can calculate, that is V2 naught minus V2. The voltage across secondary at no load minus the voltage at secondary at full load. This change is expressed as percentage of the no load secondary voltage to express the regulation. Lower value of regulation means lesser fluctuation of the voltage across the loads. If the transformer is ideal, then definitely this difference of V2 naught minus V2 will be equals to exactly 0 if the transformer is ideal. Okay, because in ideal transformer there will be no leakage fluxes. If there are no leakage fluxes, then definitely there will be no leakage drops. So whatever primary voltage is sent to the primary winding, that will be fully impressed across the secondary winding, irrespective of the type of loading, right? So since the transformer is not ideal, the transformers are not ideal in practice, the percentage regulation can be expressed by this relationship, V2 naught minus V2 by V2 naught into 100, the percentage voltage regulation for practical transformer. And that can be understood from these two. One is the equivalent circuit of the transformer referred to the secondary, the approximate equivalent circuit referred to the secondary, And secondly, the phasor diagram referred to the secondary. Right, approximate equivalent circuit means the entire primary side is transferred to the secondary, first of all, and these two are the total equivalent resistance and reactance of the transformer respectively, keeping the secondary winding impedance as well as the primary winding impedance referred to the secondary side. That means this RE2 means R2, the secondary winding resistance, plus the primary winding resistance referred to the secondary side. That means this is R2 plus R2 by S square. R1 dashed is R2 by S square. The primary winding resistance referred to the secondary side. Similarly, XE2 can be determined, right? And these two are total impedances of the approximate equivalent circuit of the transformer. This V20 is the no load voltage, and V2 is the load voltage. That means when the switch is open, V20 will be developed across the load side, where Z2 is the load impedance. And when the switch is closed, definitely V2 will be developed across the load, Z2. And what is the phasor diagram? Say V2 is taken as the reference axis. V2 is the load voltage at the rated load, at the full load. And I2 is the load current. I2 is the load current which is lagging by the load voltage V2 by the angle theta 2. Theta 2 is the power factor angle here, right? Because we are using inductive type of load, we are using lagging power factor type of load. So current I2 will be lagging by the voltage V2. Now I2 RE2 is the resistive drop across this resistance. This vector will be in parallel with the current vector I2. And I2 XE2 is the reactive drop across this reactance XE2. That will be the quadrature component. That means this reactive drop will be perpendicular on the resistive drop. And what is the resultant? Resultant is I2 Z2, I times impedance, right? So if you join the resultant with these two vectors, V2 and I2 Z2, you will get V2 0. That is the no load voltage of the transformer. And we can see that for lagging power factor type load, for inductive type of load, this V2 0 is having more magnitude compared to V2 from the phasor diagram. You can see that V2 is lesser than V2 naught. So what is the percentage voltage regulation? It is V2 naught minus V2 by V2 naught. What is V2 naught? It is OC. From the phasor diagram, V2 naught is OC and V2 is OA. V2 is OA. So it is OC minus OA by OC into 100, the percentage regulation. Now OC is equal to OD. OC can be equals to OD if you consider very small delta. If delta is very, very small, then OC will be equal to OD. And delta should be very, very small because V2 0, the no load voltage, should be in phase with V2, the load voltage. Right? Okay. There should not be much voltage fluctuations between the no load and full load conditions. Right? Right. So voltage regulation signifies that lesser voltage difference between these two phases, no load and full load. So if this delta is more, what does it signify? That there will be a huge voltage difference between no load and load. That means in that type of transformer design, the voltage fluctuations will be more. will be high. That is not desirable. So this delta should be very, very small, assuming that this vector OC is superimposed on the vector OD. So assuming this OC minus OA is just like OD minus OA, which is equals to AD. OD minus OA. This is OD, this is OA. So OD minus OA is just AD, which is again equals to AE plus ED. AD is just equals to AE plus ED. Okay. Now what is AE? It is I2 RE2 cos theta 2. Look at the phasor diagram. If this angle is theta 2, then definitely this will be theta 2 because these two lines are parallel. Right? So this A is just I2 RE2 cos theta 2. It is the in phase component. Considering AB as the resultant, AE is the cosine component of AB, right? So AE is I2 RE2 cos theta 2. And what is this component? DF. DF is the sine component. This component. If you draw a line like that, it will be just parallel with this line, right? So this component is called the sine component of this vector I2 RE2 AB. Next come to ED. ED. What is ED? ED is I2 x e2 sine theta 2. What is this vector? BC, it is I2 xc2, right? It is I2 xc2, right? And just follow these two components. This is theta 2. This is theta 2 because this is theta 2. Angle EAB is theta 2. That's why angle BCD is theta 2. And now follow this vector BC. What is BC? BC is I2 xc2. It has got two components. One is called the in-phase component, that is CF or CD, and one is called the quadrature component. Say this is CC dashed, right? So this CC dashed, this vector is just parallel to BF or parallel to ED, right? So what is CC dashed? What is CC dashed? It is I2 xe2 sine theta 2. Because what is CF? It is I2 xe2 cos theta 2, the cosine component. So this CC dash will be the sine component of this vector I2 xe2, and CC dash is parallel to ED. So ED is also I2 xe2 sine theta 2. Now what is the voltage regulation? It is OC minus OA by OC. Just put the values of OC and OA. OC minus OA. OC minus OA is this, divided by OC. What is OC? It is OD. It is C. So this voltage regulation has got two expressions, has two terms. One is I2 RE2 cos theta 2 by V2 naught, and second one is I2 XC2 by sine by V2 0 into sine theta 2. IR by V into cos plus IX by V into sine. This one. Right? Now, since we have taken this phasor diagram of transformer referred to secondary, we have got this expression. If we can draw the transformer phasor diagram referred to the primary, then also we can develop the expression of voltage regulations. So in that case, you need to change the parameters in terms of their turns ratio. Okay. But otherwise, this is the expression of voltage regulation. And further, you can express the voltage regulation in terms of this epsilon r and epsilon x. This epsilon r is just this IR2 into by V20, and epsilon x is I 2 into XC2 by V20, so that we can further express voltage regulation, which is also called as per unit voltage regulation. Why I have used this term per unit, you will not understand this per unit system right now, because it's a huge topic that is not possible to discuss within this short interval. So per unit means, just for the timing, you understand the per unit system in voltage regulation mainly describes the per unit resistance or per unit reactance of the transformer, as denoted by epsilon r and epsilon x here. That means this term I2 RE2 by V20 as epsilon r, and the reactive drop I2 X2 by V20 as epsilon x, right? So that you can represent the voltage regulation or per unit voltage regulation with a simple format, with a simple form, right? And you can see why it's called per unit. See, IR, what is that? It's a voltage drop. I2 RE2, it's a voltage drop at rated condition. At rated condition, because this I2 is nothing but a rated secondary current, the full load secondary current, when the load is connected. And what is V20? We have assumed initially it's the voltage across the secondary when no load is connected. So it's called no load transformer output voltage, right? So it's just the ratio of the full load voltage by no load voltage multiplied with a cosine term, right? So this full load by no load voltage, this type of ratio is actually termed as epsilon r and epsilon x for resistive and reactive drops respectively, to simplify the expression of voltage regulation, which is further described as per unit voltage regulation. Okay, so finally percentage regulation is epsilon r cos theta 2 plus epsilon x sine of theta 2. And this is the graph showing the percentage regulation versus the power factor. Remember that we have drawn this phasor diagram considering lagging type power factor, because the load current I2 is lagging by the voltage, right? So for this type of phasor diagram, we'll get lagging type power factor. So voltage regulation is positive. See, as the power factor is, decreasing from unity. So this center point is taken as a unity power factor. So as the power factor is decreasing, because we have taken lagging power factor, so this is 1, so 0.8, 0.6, 0.4, 0.2. As it is decaying, the voltage regulation is improving, right? Similarly, if you consider the leading type power factor in the phasor diagram, if you consider this, no, my current I2 is leading by this voltage, then definitely there will be change in the phasor diagram, there will be change in the expression of per unit voltage regulation. In that case, if you plot the percentage regulation versus power factor, you will get this type of characteristic curve. Okay, so voltage regulation will be actually negative. The voltage regulation will become negative if the secondary terminal voltage is more than the no load voltage. This will be only possible for leading type power factor, right? We have got more no load voltage V20 compared to V2, the secondary voltage, because of this phasor diagram, because we have taken the lagging type load. Okay, considering leading type load, considering leading type current I2, you will see, if you draw the modified phasor diagram, you will see that V2, this voltage will be more compared to this V20, compared to the no load voltage. So in that case, for leading type power factor, the regulation will become negative. So you will get the reverse characteristic curve. And one more thing, this block diagram is showing the single phase transformer basic block diagram. This is the core it has got two limbs, limb 1 and limb 2, around which the windings are wrapped. So these are basically windings, right? So exactly near the core, the low voltage windings are wrapped in practice, around which the high voltage windings will be wrapped. So what happens actually, the total low voltage windings will be distributed in the two limbs. So first, just after the core, the low voltage windings will be placed, and around which the total high voltage windings will be distributed in the two limbs. Fine. Fine. This is done only because to avoid the high insulation cost. For low voltage windings, the insulation will be less. So lesser insulation cost is required. That's why we mainly choose low voltage windings near the core material. Also, you can design your transformer keeping the high voltage windings near the core, but in that case, more insulation will be required. That will cause more transformer insulation cost. Okay. Do you have any questions up to this?
No, ma'am.
Okay. So today we need to
One
stop
question,
here
ma'am.
because time is over. Next day I'll start with transformer efficiency. I have already sent this PPT.
Ma'am,
Yes.
ma'am, in the hysteresis curve, I have a question.
Yes.
Ma'am, I have a question in the hysteresis curve.
Yes. Yes. Please.
Ma'am, that coercive
Coercive force.
yes, yes.
OC. This is coercive force. OC.
Yes, ma'am.
The amount of field intensity HM required to make the residual magnetism zero. That is called the coercive force.
Okay, okay.
Because see, at point C, there is no flux density or field density. Though we have the field intensity of HM of amount OC. So it's this amount of force is required to turn down this magnetism that was there in the material amount OB. So,
yes, ma'am.
okay. This is coercivity, HC, mainly denoted by HC, and OF is also coercive force. That is also required to make the flux density OE to be zero.
Yes, ma'am. Understood.
For both direction of supply current. Any more questions, students? You can ask me. I have already sent this PPT, so please go through the first part of this transformer. After this week, I'll send one more PPT from transformer, including the rest part, the auto transformer and three-phase transformer connections, etc. And after the completion of this transformer, probably I'll send one assignment based on transformer. Okay. Transformer and also the module 5, power converters. So please be ready with these two modules. And tomorrow, in the tutorial class, we'll solve problems from transformers, numericals from transformers. Okay, I've seen that in your syllabus, the open circuit and short circuit tests are not there, right? But all in your laboratory curriculum, these two tests are there. But since in theory subject, you do not have these two tests, so maybe I'll not cover the theory portion of these two tests in the class right now. Maybe after completion of all the modules, if you want, I can explain, but in the tutorial class, I'll try to cover one numerical from open circuit and short circuit test, because these two tests are very, very important tests in transformer. Because without knowing these two tests, we will not be able to understand how actually the losses are getting evaluated. Okay, so tomorrow we'll solve numericals. So before that, please try to go through the PPT at least once.
I mean, CA3, we will be having written examination or assignment only?
CA3. Before CA3, you have CA2, I guess, right? I don't know.
Ma'am, CA2 is already done.
CA2 is already done, ma'am.
CA2 is already done. Okay. Okay, so CA3, right now I can't tell you that CA3 will be based on any other internal test or it will be based on assignment. But I can tell you that probably after the completion of transformer, I'll send you one assignment based on module 5 and this module 3, transformer and power converters. Right?
Okay.
So maybe it will be an assignment based evaluation or it will be an internal based evaluation. That I can't tell you right now because I do not have any information from College Authority. Okay?
Okay.
Okay, ma'am.
Okay. So let me take your attendance now. Roll number 1.
Present, ma'am.
2.
Present, ma'am.
3.
Present, ma'am.
4.
Present, ma'am.
5.
Present, ma'am.
6.
Present, ma'am.
6.
Present, ma'am.
Okay. 7.
Present, ma'am.
8.
Present, ma'am.
9.
Present, ma'am.
10.
Ma'am.
Pushpendu.
Yes, ma'am. Yes, ma'am.
11.
Present, ma'am.
12. Sattam. 13.
Present, ma'am.
14.
Present, ma'am.
15.
Present, ma'am.
16.
Yes, ma'am.
17.
Yes, ma'am.
18.
Present, please, ma'am.
19.
Present, ma'am.
20.
Present, ma'am.
21.
Present, ma'am.
22.
Present, ma'am.
23.
Yes, ma'am.
24.
Present, ma'am.
25.
Present, ma'am.
26. Onindo. 27.
Present, ma'am.
Onindo is present?
Yes, ma'am.
Okay. 27.
Present, ma'am.
28. Apurv.
Present, ma'am.
29.
Yes, ma'am.
30.
Present, ma'am.
31.
Yes, ma'am.
32.
Present, ma'am.
33.
Present, ma'am.
34. 35.
Present, ma'am. 34 is. Ma'am,
Okay.
34.
35 is present.
Yes, ma'am.
36.
Present, ma'am.
37.
Present, ma'am.
38.
Present, ma'am.
39. Shagnik Mukherjee. 40.
Present, ma'am.
41.
Present, ma'am.
42.
Present, ma'am.
43.
Present, ma'am.
44.
Present, ma'am.
45.
Present, ma'am.
46. 47.
Present, ma'am.
48.
Present, ma'am.